Today let us discuss a fundamental concept. The problem is two entities need to prove to each other that they possess the same secret key. The two entities we shall call the PCD and the PICC. And in this pink oval here are the secret keys. As you can see in the picture, they have the same value. These two entities needs to prove that indeed they have this value. Now, you will say, well, one of the entities, for example, the PCD, why can't just he send this value, and if they are equal, then they're equal, right? The problem with that approach is if the PCD is going to send this key and he is sending it to an imposter party, like it's not really the entity that he wants to communicate, but another imposter entity. The imposter entities will going to pretend, yeah, I have the same key, and the PCD will think that okay, he is the one. So this need to prove the possession of same key is not so simple. You could not send the key, but yet you need to prove that both of you have the same key. Secondly, the communication medium, Wi-Fi, USB, etc., is insecure and there is an eavesdropper listening. So if you send this key in plain format, the eavesdropper is going to intercept it and will discover the key. So now let us discuss how is this possible. An analogy to this situation that came to mind is two lovers like Romeo and Juliet. They need to prove to each other that they love each other, right? And we know that saying I love you will not prove anything because love is not just words, it needs to be computed in order to be believed. So that's the analogy here, and we are now going to see how cryptography and the computation that I will describe here can prove this secret key without sharing the key. The first step is both sides shall generate a random number, and we can see here the PCD generated this 8 bits random number. The PICC generated its own 8-bit random number. Second, the PCD shall send a signal. He could light a fire, he could make an explosion. It's just a signal, it has no content. We shall call the auth command. There's no content in this except for the signal itself. So the random data is not in this command, the auth command, no. It is just a signal. The signal to begin the business of proving procedure. Okay. When the PICC receives the auth command, the PICC shall think that shall XOR its random value with a secret key, and This is the result. And this is what it will send back to the PCD, the XOR value. The thought process here is that if the PCD indeed has the secret key, then the PCD can XOR again the data and recompute my random number. Because XOR, when you XOR again at the same time, then you go back to the original data, right? Furthermore, an eavesdropper receiving this sequence of bits will never be able to compute back the randomized value because he does not have the secret key to XOR and recompute the data. Take note that XOR is the most secure form of cryptography. It is unbreakable if your secret key is equal to the size of your data, then you have an unbreakable encryption. Take note. We're just using 8 bits here for simplification. Okay? So do not underestimate XOR methodology. Now, the PCD XORing again the data indeed has recomputed back the random number generated by PICC, as you can see in the brown box here. The problem now is that PCD could not send it back to PICC to prove that he knows the random number. So at this point, nothing is proven yet. And also, the PCD could not just echo back this same sequence of bits because, like I said from the beginning, an impostor can do that. So to avoid that impostor scenario, the PCD shall rotate left the bits, and this is the result. And these rotated bits shall be XORed and is the one that it will send back to the PICC, thus proving that PCD is able to guess the random value PICC. And to optimize the communication, the PCD also just concatenate its random value, and together these 16 bits XORed back, XORed with twice with a secret key is what is sent back. This is an optimization to save the back and forth communication. So the first half of the 16 bits is the randomized value, and the other half is the random value of the PCD, as you can see in the diagram. These first half, second half, rotating left, rotating right, these are a priori knowledge that both of them should know in advance. Okay, and in the cryptography, these are called cipher suites, sequence of operations and procedures that should be known by two parties in advance. Otherwise, no encryption, no cryptography is possible without this a priori understanding. So, with the understanding that this first half is random number, then PICC just needs to shift right again, and if the computed result is equal to its randomized value, then PICC indeed has proven that yes, PCD has the key. Now, this is just one half of the story. Only PICC has proven that PCD has the key. On the other hand, PCD has not yet got any proof that PICC has the same key. And that is what the final arrow is for. So the PICC again does a shift left of what it receives here, and that is being XORed again with a secret key and send it back to the PCD. The same principle, guys. Shifting left and XOR. and then the PCD shall XOR it again and we compute the value, and then he does a shift right. And if what is shifted right matches its own random value here, then PCD can finally say that indeed, yes, PICC has the same key, and this completes the 3-pass mutual authentication. So the final result is that PCD and PICC has proven to each other that they have the same key without sharing the key and without leaking this key in an insecure medium by a possible eavesdropper. That's it.